Whatever the universe was at the very beginning, some 13.7 billion years ago, we think it was tiny, smaller than an atom, about as small as the proton at the center of an atom. And then something happened, triggering the most colossal explosion in history. In a billionth of a billionth of a billionth of a second, the universe grew from the size of that tiny point to something billions of miles across. This colossal blast created everything, all the matter we see in the universe today.
It was not just an explosion of material into an empty universe that was sitting there waiting to be filled. It was the explosion of space and time into existence to begin with.
And that's what trips most of us up. Before the Big Bang, there was nothing, literally nothing. And the black void of space is something. So is time.
To ask where the Big Bang occurred is meaningless because there was no space.
In physics, the study of quantum mechanics is the study of the smallest elements and forces of matter, and how they react and interact, and thus create all that we know. In some experiments, they behave exactly like a particle. In other experiments, the very same elements behave exactly as a wave should. But how can this be? Waves and particles are two entirely different forms of reality. Atoms are made up of even smaller bits, or particles, or wave packets, or substances of reality. And it appears that these elements are made up of even smaller elements and or energy forces. But we've also discovered that these small parts interact in ways in which we cannot describe by known laws of the universe. Quantum laws appear to be very different from the classical laws of nature. The quantum particles seem to be operating outside of our reality of time and space. We know, for example, that when one of these small parts is manipulated or stimulated in any way, it seems to instantly affect and cause reaction in the other small parts associated with it, which do not otherwise appear to be connected by any force or even connected by yet another small part. It doesn't even matter if these small parts are separated by great distances. They still react instantly to the stimulus applied to another part. It is as though they are tied together by some invisible force or energy, or some would even speculate, some unknown and immeasurable thought or communication process. This phenomena is known as the entanglement theory. This gives rise to the philosophical thought that since everything elemental was created or came into being in one big instant, then everything at the subatomic level is still connected or entangled and somehow reacts together. In addition to these strange phenomena, we have no way of exactly and precisely knowing where and when one of these small parts will be in any particular location or state. We can only speak about their location or state of existence in probabilities. This is known in quantum physics as the measurement problem. Also, it seems apparent thus far, the smaller you go in the observation of these small parts and their interactions, the less and less of anything that we know as real seems to exist. Time and space and matter seem to disappear into nothingness. Philosophically, this is very challenging, since we live in a real world with tangible objects existing in a time-space reality, yet we know that our reality is made up of the very particles which themselves seem to recede into nothingness, and they operate outside of time-space realities and natural laws of our material world. But how can this be? Welcome to just one more of the many conundrums of quantum mechanics.
A recent scientific study undertaken by the University of Bonn in Germany suggests that the universe could be one giant computer simulation. Moore's law dictates that computing power doubles approximately every 2 years, and eventually we're going to reach the stage where computers can artificially create a virtual reality which is indistinguishable from our own. Wired magazine: cosmic rays offer clue our universe could be a computer simulation. If recent measurements of cosmic ray particles are correct, then we may have the first evidence that the universe as we know it is really a giant computer simulation. And basically, what these scientists discovered is that when cosmic rays fly through the universe, the energy that they lose is, quote, consistent with the kind of boundary that you'd find if there was an underlying lattice governing the limits of a simulator. And in this article they make an analogy with a chessboard. Cosmic rays behave like chess pieces on a chessboard. You can't move them less than one whole space on this lattice structure which they've measured. So these uniform rules governing the movement and behavior of cosmic rays suggest that they are performing as they would if they were trapped inside a giant simulation. Now, they've only got the computing power at present to test this on a tiny scale, so it's far from conclusive, but the early indications really do suggest that our entire universe could be nothing more than a computer-generated simulation. And the New Scientist interviewed Silath Bean, the chief scientist there at the University of Bonn, involved in this project, and the article concludes that, quote, the answer, statistically speaking, is that we're more likely to be living in a simulation. Here's an MIT Technology Review piece, the measurement that would reveal the universe as a computer simulation. Quote, so if our cosmos is merely a simulation, there ought to be a cutoff in the spectrum of high energy particles. It turns out there is exactly this kind of cutoff in the energy of cosmic ray particles, a limit known as the Greisen-Zatsepin-Kuzmin or GZK cutoff. So they've measured it, they've measured the effect on these cosmic rays, which basically suggests that they are trapped inside this giant computer simulation that we know as the universe. Are we all walking around in someone else's dream? Unfortunately, we're all going to be long dead before anyone really knows for sure.